A great pleasure to introduce Rebecca Willett, who is giving the Kirk Distinguished Lecture Fellowship talk. A few words about Rebecca before I hand the word over to you, Rebecca. Rebecca is a professor of statistics and computer science at the University of Chicago. Her research is focused on machine learning, signal processing, and large-scale data science. Rebecca has received for her work, there is the NSF Career Award in 2007, an Air Force Office of Scientific Research Young Investigator Program Award in 2010, and she was named a Fellow of the Society of Industrial and Applied Mathematics only this year. He's a co-principal investigator and member of the Executive Committee for the Institute for the Foundations of Data Science, helps direct the Air Force Research Lab University Center of Excellence of Machine Learning, currently leads the University of Chicago's AI plus Science initiative. PhD in Electrical and Computer Engineering at Rice University in 2005, was an assistant, then tenured associate professor of Electrical and Computer Engineering at Duke University in 2013. Was an associate professor of Electrical and Computer Engineering, Harvey D. Spengler Faculty Scholar, Fellow of the Wisconsin Institutes for Discovery at the University of Wisconsin-Madison from 2013 to 2018. The Kirk Distinguished Lecture, our research program on the mathematics of deep learning. Kirk Distinguished Lectureship Program has been established in 2019 following a generous donation from the Turner Kirk Charity Trust. Highlights the work of field-leading figures in mathematics, particularly chosen underrepresented groups within higher mathematics. I hand the word over to you, Rebecca, to give a lecture on machine learning and first problems in computing.
Thank you so much, Carola. I really appreciate the invitation. This is a huge honor for me, and I'm really grateful to have this chance to talk with you all about some of the work that we're doing, and do apologize sincerely about the time confusion. So as Carla mentioned, I wanted to talk about some work that I've been doing in my group, and that's been a growing part of the machine learning community on trying to understand the role that machine learning can play in trying to solve different inverse problems in computational imaging. And this has been a long-standing interest of mine. I remember even in grad school, some collaborators at NASA showing me this video. And in this video, what we see are different images collected by different satellites, all reflecting different properties of the sun. And you can see that they show different resolutions, they're showing different wavelengths of light, and they're all collected in different ways. And so the goal of heliophysicists, or these NASA scientists, is to try to take this complex imaging data and try to understand something fundamental about the physics of the sun. So you can see in this slide, one of the instruments that's being used is something called RESI. And if we look and see how that data is collected, it's a pretty complex operation, a pretty complex telescope that involves multiple different coding disks, all within this tube that's constantly rotating. And so they might be interested in trying to understand some sort of solar flare behavior, but they don't get a direct image. Rather, for each one of these different coded disks, they would get a time series of different counts of photons. And from those 9 different time series, they would work to try to actually construct this image. So this is a quintessential example of computational imaging, where we're ultimately interested in some sort of scene or image, but we don't get to observe it directly like we would with a smartphone. Another classical example arises in CT, or computed tomography scans. So in this setup, imagine that we were trying to take a scan of someone's head to see some information about their brain. A scanner would have a collection of different X-ray transmitters that would all shoot X-rays in parallel in this example through the brain. And then what we would record on a series of detectors on the other side is how much of that initial X-ray energy is transmitted through for each one of those beams. And then what we can do is we can actually rotate those beams and collect the same kind of measurement from all these different angles. And so in the right here, what I'm showing are the measurements that we collect for each one of these different rotations. And this is often called a sinogram. And so again, what we'd like to be able to do is to take this indirect information, this sinogram, and from it reconstruct this image of the brain. And this again is an example of computational imaging. So these and many other problems can all be represented mathematically or approximated mathematically as a linear inverse problem, where the image that we're interested in is denoted X, and we observe some linear operator A times X plus some noise, and we call those observations Y, and our goal is to recover X from Y. And so in addition to the examples that I just showed you, we could imagine problems such as in painting, where we've got a camera where some of the pixels are broken or some of the sensors are broken, and we need to recover the missing pixel values. Another example is deblurring, where someone collects a really blurry picture and we want to remove those blur artifacts in order to get a nice, crisp, and interpretable image. Super resolution, or reconstruction of images from MRI, where our measurements correspond to a subset of the Fourier transform coefficients of the image. So in all of these examples, this matrix A is what we call a forward model. And basically what it does is it tells us what are the physics of the imaging system. How is the true image X that we're interested in mapped to the measurements Y? So it, for instance, would correspond to a subset of rows of a Fourier transform matrix in the MRI setting. So when I write things like this in this sort of linear system of equations framework, then I think many of us would immediately think, well, we could just find a good image X using a least squares approach. So for instance, imagine that I've got a blurry image that I want to deblur, and A reflects a model of what that blur looks like. Then the least squares approach would be to say, well, let's search over all candidate images X and try to find the one so that if I were to blur that image using A, then it's as close as possible to Y, my measurements. And so we can do some simple algebraic manipulations. And what we see is that the closed form solution to this minimization problem is our true image X that we're really going after, plus another term. And this other term depends on what the blur is and what our noise is. So if we have zero noise, which is the case in this image in the upper left, and we try this least square solution, it works great. But if we have even a small amount of noise that is maybe even imperceptible to the human eye, it can still lead to huge distortions. And the issue is that even when this epsilon is small, because of the structure of this matrix representing the blur, when we try to do this inverse operation, we can get huge numbers. And so they take even a tiny amount of noise and magnify it by a large amount. And so just solving for least squares is insufficient. This problem is just inherently ill-posed. And so one of the approaches that's very popular for addressing this is regularization. And one of the most widely known regularization approaches is Tikhonov regularization, or in the statistics literature, it would be called ridge regression. So here, the idea is that we're going to, again, search over all candidate images X and find images where if I blur them using my known blur model, it is very close to what I've observed. But at the same time, I want to make sure that whatever image I use as my estimate isn't going to have huge pixel values like this distorted reconstruction does. So we're saying we know that this problem is inherently ill-posed, so let's make sure that none of the pixel values go too far astray. And again, we can write down sort of a closed form expression for this, and mathematically we can analyze it in order to show how including that small bit of regularization, results in a suppression of this noise term. And so if we were to apply this, we can see that we get significantly better results even with noisy inputs. It's not perfect. You can see that there's some ringing artifacts and it still looks a little bit blurry, but nevertheless, we've achieved through this regularization process a lot of robustness to the noise in the data. Okay, so the question then becomes, how can we design alternative regularizers to this very simple Tikhonov regularization framework? And this is something that engineers and mathematicians have been studying for many decades. And there's been a number of different proposals out there. So generically, the idea is that, again, we want to search over candidate images X and find one that is a good fit to the data if we go through our forward model A, and which has a small value for some regularization parameter. And we use this regularization parameter as a way to model the kinds of geometry or structure that we might see in images. So for instance, we might say, well, if I were to take a wavelet transform of an image, then most of those wavelet coefficients should be very close to 0. And so I can build a regularization function that reflects that prior knowledge or reflects that model. Or similarly, I might say, well, if I were to take first order differences between neighboring pixels, most of those are going to be very close to 0 because there's lots of regions in the image where the brightness is not changing very dramatically. There's only a small, relatively small number of locations where there's a sharp edge or boundary. And so again, I can build a regularization function that measures essentially how big these different first order differences are and tries to ensure that whatever estimate that we find doesn't have lots of large first order differences. And there's other models that will reflect the fact that within a given image, we might have a high degree of redundancy. So if I were to split the image into patches, a lot of those patches might have kind of similar geometric properties. And so again, I can build regularization functions to reflect that. But there's been a growing trend in the imaging community and in the machine learning community on saying, well, instead of us kind of sitting back and imagining what kinds of geometric structure is in images, and then designing a regularization function based on that, can we instead use training data to learn how to reconstruct images? So if I had a whole bunch of examples of images X and distorted images or indirect measurements Y, then could I use those pairs to train, for instance, a neural network that maps a set of measurements to an image estimate and try to choose the weights of this network so that the image estimate is, on average, as accurate as possible? So this is a generic idea that's been explored in a lot of different directions. And in fact, Carola has done some really amazing work in this space. And in the bottom right here, I've cited a review paper that she wrote with some collaborators a couple of years ago that I think does an excellent job of laying out some of the key mathematical issues that arise here and some of the different frameworks that people have proposed. And contemporaneously, we wrote a related review paper that describes some of the prevailing themes in this space. So certainly because it's an active area, I won't go into all the different methods that are being developed, but I did want to give you a flavor of the different kinds of approaches that people are considering. So the basic framework is the following. We imagine, like I said, that we've got a whole bunch of different image and measurement pairs that correspond to a known forward model A. And then what we want to do is we want to train a neural network, and I'm going to represent that network by f sub theta. So I can think about theta as corresponding to all of the weights of the edges in this neural network. And f sub theta just corresponds to the mapping from the input of the network to the output of the network. And so what I want to do is I want to choose the weights theta so that on all my training samples, if I were to send yi through this network, then it outputs an estimate xi hat, which is as close as possible to xi. And we measure that, for instance, using squared error. And so then in the future, when I get a new image data set or a new set of measurements y, then I can feed that through my trained network and get an estimate x hat. So here's an example with MRI where these white dots here in the y space are indicating what parts of the Fourier transform do we have measurements of the coefficients for. So in general, when people are trying to collect MRI data, they want to have lots of black pixels in here because that corresponds to a very quick acquisition process. It means they're able to collect all the MRI data very, very quickly, and then they can get more patients through, or they can get more images more quickly. And so this is just indicating how few of the Fourier transform coefficients of the image we're able to collect. And so we take those limited number of Fourier transform coefficients, feed it into our network, and then get an image estimate out. So one approach that is very popular, and that Carola, for instance, has spent a lot of time studying and trying to understand from multiple different perspectives, is what I call a model agnostic approach. And what I mean by that is that the forward model A is not used directly to construct the architecture of the neural network. So for instance, in the context of super resolution, I know that I'm observing a low resolution version of my image, but I don't have necessarily a really accurate estimate of what that sort of low resolution to high resolution or vice versa map looks like. And so I don't assume that I know A exactly, but rather I just do some simple bicubic interpolation to get an initial image that's at roughly the resolution that I want. And this is pretty easy to do, but as you can see, it can give some pretty ugly looking images, right? It's really blurry, there's some blocking artifacts. It just doesn't the quality that we want. But given a whole bunch of images like this, then what I can do is I can train a neural network to essentially remove those artifacts. So it's sort of like a denoising neural network, only it's trained on these blurry and blocky images to remove those types of artifacts. And so for problems like deblurring or super resolution, this can be extremely effective. But there are other problems where the matrix A might be far more complex. For instance, in this MRI setting where it corresponds to a subset of Fourier coefficients. And so in those settings, this approach can be effective, but it can require really huge amounts of training data. Because what we're relying on is that our training data is going to allow us to learn not only something about the geometry and structure of images, but also something about the relationship between my images X and my measurements Y. Right? If I don't actually use that knowledge, then I'm forcing my neural network to sort of figure that out on the fly. And so learning that additional information can require significantly more data. And so this leads to, I think, a pretty fundamental and central question, which is, can we design this neural network, F theta? Can we choose sort of the architecture or the design of the neural network in a way that reflects our knowledge of the underlying physics of this matrix A? And so I'm going to talk about several approaches to that. And one particularly popular approach is to adopt this regularization perspective that we talked about in classical settings. So again, we said, you know, the classical approach would be to imagine that we know a good regularization function R, or that we can mathematically come up with a good model. And then we'll search over all images X to find one that's a good fit to the data and has a small value for this regularization function. And so what we might do is we might say, well, instead of choosing the regularizer ahead of time based on some mathematical model of geometry and images, can we learn it from training data? So to understand how this might work or what it might look like, let's take a step back for a moment and say, well, what would I do if I knew a good regularization function R? How would I actually solve this optimization problem? So there's many different methods that we could consider, and I'm going to describe one here corresponding to proximal gradient descent. And the idea is the following. So we start with some initial estimate of the image X, and this could be something like A transpose times Y, and we've got some step size. And then we just alternate between two different steps. So in the first step, what we're doing is we're taking our current estimate and we're just giving it a nudge in the direction of being a better fit to the data. And so this corresponds more precisely to taking this squared error term here and taking a step in the negative gradient of that function. Second, once we've forced our estimate to be a little bit more consistent with the data, once we've nudged it in the direction of having a better fit to the data, it might have some artifacts arising from the noise that's in the data. And so our next step is to do a denoising operation, where we say, let's search over all images X and find one which is a good fit to this intermediate estimate that I just calculated, but which also has a small value for the regularization parameter. And so people have looked at a variety of different sort of denoising steps here. And in general, this is called a proximal operator. It just corresponds to the denoising that I just described, but that's why the method is called proximal gradient descent, because we think of this denoising step as a proximal operator. And visually, we can think of this whole process using a block diagram where I start with an initial estimate, and then I do a data consistency step, and then apply my proximal operator, data consistency, proximal operator, and I keep on doing that until I converge. So this is what I would do if I knew of a good regularization function R of X, like a measure of total variation or something. But we are interested in settings where we don't know a good R and we want to learn it. So one approach that you could use, which is called the plug and play approach, says, let's just replace this formal proximal operator corresponding to a known regularization function with a neural network. For instance, a convolutional neural network designed for denoising. So we train a neural network to input noisy images Z and output denoised images X. And so if we can have a good trained denoiser, then we can just plug that into this framework that I've been describing, so that now we alternate between a data consistency step and then a neural network denoiser, data consistency step, neural network denoiser. And there's been a lot of work done in this space, especially trying to understand the convergence properties of it. So what has to be true about whatever denoising method that we're plugging in here in order to ensure that this actually will converge to something and not diverge. So this is an exciting approach, and in particular, you can, if you've got lots of data, get very good reconstructions using this approach. So here's an in-painting example where I've missed a whole bunch of pixels in the center, and I need to learn to fill in a nose and an eye. And so if I had 80,000 images of people's faces that are kind of centered in the middle of the image like this, then I can train a network to do good denoising, and I can get a good in-painting reconstruction that looks very high quality here. But if I were to use a much smaller number of samples, a number of samples that's more in line with what we might have in, say, a medical imaging setting, then all of a sudden this breaks down and we get much worse reconstructions. So why is this? We're using the forward model A when we have this data consistency step. We've grounded everything in optimization methods that have been studied and understood for decades. Is this just a fundamental limitation of what these methods can do or not? And what I would argue is that it's not a fundamental limitation at this point. And the reason that I would say that is the following. When we learn how to denoise images, what we're essentially learning is some sort of like prior probability model over the space of images. We're saying, well, what kinds of images are more likely and what kinds of images are less likely? But in the context of this in-painting problem, for instance, when we learn about the structure of whole images, that represents all kinds of information that's totally irrelevant to our in-painting task. So if my job is to fill in the fact that she's got, a missing eye and a half and a missing nose, well, it really doesn't matter whether I've got a good model or whether I've accurately learned how to represent the backgrounds of this image. If I try to figure out how to do great denoising globally, then I end up having to learn a whole lot of stuff that's irrelevant to this inverse problem I'm trying to solve. And in contrast, what I'm really interested in is a conditional probability distribution. I want to know what's the distribution of all the pixels I'm missing, and I represent that as the stuff orthogonal to A in the image, given the stuff that I actually observe, A times X. And this is a much easier problem in many cases. In many cases, this conditional density can be learned with many fewer training samples than estimating the full density up here. This could be because that full density is a much smoother thing and less complex, or it could also be lower dimensional. And so all of this is to say, it's possible to learn a distribution that depends on this forward model A with a lot less data. And that suggests that if we do know what this forward model A is, then somehow it should be used during the training. So with everything we've done so far, we have not used A during the training. So there's another class of approaches called deep unrolling that try to use A during the training, and this is how they go about it. They would say, again, we're going to start from this basic framework of trying to find the image that's as good a possible a match to the data as possible through this forward model A and has a small regularizer R. And the whole top of the slide is just showing the proximal gradient method that we described before, where we've plugged in a denoiser. The key distinction between what I'm talking about now and what we've done before is that now we are going to think about what is going to be the output of this procedure after a fixed number of iterations or blocks K. K is typically small, like on the order of 5 or 10. And the idea would be that instead of trying to train a denoiser ahead of time and then just dropping it in, what I want to do is I want to train the weights or learn the weights of this denoiser so that the output of this whole procedure after K iterations is as accurate as possible. So the structure looks very similar, but the training is totally different. Let me try to kind of elaborate on that a little bit more. So with the original plug and play approach that I described, we first train a network to do some denoising. So at this point, we're not thinking about inverse problems at all, really. We're just thinking about how to train a good denoiser. Then we plug that into some optimization framework, like this proximal gradient algorithm, and then we run until convergence. So the number of iterations we run, K, is determined on the fly. And in contrast with deep unrolling, we're going to choose and fix the number of iterations K in advance. We're going to say, hey, I want to design this method so that it works really well after just 10 iterations. And then we're going to construct a network that corresponds to K iterations of an optimization method. So I create this sort of block diagram at the bottom here, where these data consistency terms are a function of the forward model A. And then what I'm going to do is I'm going to train this whole big system so that the output after K iterations is accurate. And one of the reasons that I think that this is so fascinating and interesting is that I can think about this structure that I've got at the bottom as just one giant neural network where some of the weights and some of the architecture is guided by the physics of my system. So here I'm just showing 2 blocks with some ellipses in the middle. And I want to focus on this data consistency term here. So what's happening in that block, I can think of that as a neural network where all of the activations are linear and where the weights in that neural network are basically determined. The weight matrix corresponds to the identity matrix minus my step size eta times A transpose A. So what I really have here, putting this together, is one big neural network where some of the elements of the network are, and the architecture are fixed. And they're determined by our choice of optimization methods, say whether we're using proximal gradient or some other approach, what our forward model A is, and the observed image data Y. And then there are other parts of the neural network where things are much more freewheeling, where we can learn the weights using our training data. And so I think this is interesting because there's a lot of general discussion in the machine learning community about how should we design the architecture of these networks? How many layers should we have? Whether should we sometimes have linear activations, or should all the activations be nonlinear? What's the role of depth? What's the role of width? And these are all generally questions that we have a pretty limited understanding of so far, and there's a lot of active research in trying to understand that. But this particular case study is a setting where we've actually been able to say how we can use ideas from mathematics, from optimization, from statistics, and based on physical models of how our data is collected, to actually use those things to guide our choice of how the network should be constructed and what its architecture should look like. So I want to give you a related example of this in action that's coming from a slightly different mathematical framework. So again, we're thinking about the setting where we have this sort of optimization framework at the heart. But now, instead of starting from a proximal gradient method, we say, well, what if I could somehow write down a simple closed form expression for the solution? And then this has got an inverse in it, but expands that inverse using a Neumann series. So then in this expression for my estimate of the image, I can see in here that I've got a gradient of my regularization function, and I can replace that with a learned neural network. And so now I get a new architecture that, similar to before, has got some familiar elements. It's got a data consistency block that is guided by my forward model A, or the physics of the system that I'm working with. And it's also got some learned components. But in contrast to past approaches, here I'm just going to do a nice compare and contrast here. What we see is that by using this Neumann series as a starting point, all of a sudden we get these extra kinds of connections popping up, so that a small change early in an early block can be immediately felt by the output. And it turns out that by making this subtle change, by changing our starting point a little bit, by keeping this core principle that we should be incorporating our knowledge of the physics of the system by incorporating A, we're able to come up with a new method that's easier to optimize, easier to train, and performs better. So what I'm going to show you are some empirical results. First, just a little anecdotal example where we're solving a deblurring problem. So here's the true image and here's the blurry image. And we're going to do this twice, once where we've only got 2,000 training samples and once where we've got 30,000 training samples. And in the top row, I'm showing you different estimates of the image. And in the bottom rows, in black and white, I'm showing you the residuals that have been magnified to kind of highlight what the differences are among the different methods. And so the blacker these residual images are, the more accurate the method is. And so what we're seeing here in this first column of results are the results of this Neumann series-based approach. In the second column, we get the result corresponding to taking proximal gradient descent and unrolling it. In the third column, we see this approach where we just try to take our data and directly learn a mapping from the Y's, the observations, to the X's, the image estimates. And then finally, what I call the decoupled approach, where I try to train a denoiser ahead of time and then just plug it in. And so this is not just true in this one little small image of an airplane, but it's generally true for a variety of different linear inverse problems explored on a variety of different training data sets. That in general, these top 3 approaches, which are all designed to incorporate knowledge of A into the training process in a principled way that takes ideas from statistics and optimization, have a significant advantage over approaches that don't use that knowledge, especially in settings where we really have small amounts of training data. And so the key takeaway message here is that in general, methods that are trained for a specific forward model A can often outperform more model agnostic training that doesn't take A into account. And here's just an example of these ideas in the context of MRI for brain imaging. So here's the original image, and down here, like I said, we've got these black and white bars indicating which Fourier coefficients get measured or not measured. And so roughly about half of the pixels in here are black. So we're roughly measuring about half of the Fourier coefficients of the image. On the top row, I've got various different reconstructions, and then below that, I've got their residuals or their error maps. And I'm comparing 3 different methods which are learned versus a 4th method, which is based on total variation regularization, which is a more kind of traditional baseline approach. And we can see that they're all doing quite well, though numerically, the methods that are based on machine learning are a little bit better than the methods based on total variation. But in addition, and pretty notably, the amount of time it takes to compute the total variation estimate is 350 seconds. In contrast with these methods based on machine learning, which are on the order of 5 to 15 seconds. So a huge reduction in the amount of computation time required to compute a reconstruction after we've done all the training. And this is one of the reasons why these methods are exciting so much interest. Okay, so you might ask, well, what can we do to get even better results from here? How can we improve on deep unrolling? So one idea that's been explored is to say, well, we get really good performance when we train using this deep unrolling framework that we've been just talking about so far. But then at deployment time, when I'm actually like running this in the wild and reconstructing images after all my training is finished, maybe what I could do is I could take this denoiser that I learned up above, plug it in, but run my proximal gradient method all the way until convergence. So even though I trained, say, for 6 iterations, at deployment, I could run it for any number of iterations that I want. And maybe that could even improve my performance. And so that's a reasonable question. Would this actually work? And the answer is no, it does not work. It works quite badly. So let's look at this orange curve, for instance. So in this case, we trained our deep unrolling method for using 6 blocks or 6 iterations. And then at deployment, we tried running it for a large number of different blocks or iterations. And so if at deployment we run it for 6 iterations, what we trained for, then it works great. We get an accuracy peak SNR of about 31. But if we try to run for any more iterations, then the error just starts to drop and drop quickly. And then we might train for a larger number of blocks, so K is equal to 10. And then at 10 iterations during deployment, we do great, but any more or any fewer iterations, and we do worse. And if we start trying to make K, the number of blocks that we're training on, even bigger, then the performance gets even worse in a pretty dramatic way. And this is because at some point, things just become far less stable. And so we require a lot of memory. These methods become very sensitive to small little, design decisions and how we train things. And it becomes just very, very hard to get high accuracy results when you make K much larger than 10. Another way of looking at this is pictorially. So imagine that I trained my network based on 10 iterations, but then at deployment, I run it for 10 or 20 or 30 or 40 iterations. And what we see is that as we continue to run this, it does not converge. And in fact, it introduces some pretty horrific artifacts. So what could we do? We can't just run it for more iterations at deployment time. And we also can't just use more iterations during training time. Both of those things actually make things worse. So what can we do that's better? So I'm going to propose an alternative approach that's based on a fixed point perspective. Okay, so if I've got a function f, a fixed point x star is just a point where if I compute f of x star, that's equal to x star. And so when we think about these optimization methods like proximal gradient descent, what they're doing is they're actually finding a fixed point of a particular function f. So for instance, we talked about this kind of single iteration of proximal gradient descent having a data consistency term and a proximal operator. And so the corresponding function f corresponds to that data consistency step and that proximal operator. And so if I were to just continue to iterate this for an infinite number of iterations, then I would find a fixed point of this function f. And the same can be said with this kind of plug and play or deep unrolling approach, where we've got a function f that now depends on the weights of the neural network that we've plugged in. And if we were able to iterate this an infinite number of times, we would ultimately find a fixed point of this function f. And so perhaps instead of explicitly having a large number of iterations during training, which we saw works badly, we could implicitly do it. So in other words, what we could try to do is we could try to learn the weights so that, not so that it works well after a small number, k, maybe like 5 iterations is good, but rather so that after an infinite number of iterations, we get a good reconstruction. Or in other words, we want to choose the weights of our neural network so that a fixed point of this function f theta is a good reconstruction of the image. And so this takes a careful rethinking of how we actually do the training, because we don't want to explicitly have an infinite number of blocks to train through. That would require an infinite amount of memory. But we can, and in the interest of time, I'm going to gloss over some of the details here, but what we can do is we can do some implicit differentiation. So in order to train these networks, you have to be able to do gradient descent. So you have to be able to compute the gradient of your loss with respect to your parameters theta. And that requires, after using the chain rule, computing the gradient of our fixed point with respect to the parameters theta. So this is sort of a basic starting point of any of these methods. And now what we need to be able to do is to take the fact that we're ultimately interested in a fixed point and plug that in here to come up with an expression for the gradient that we can actually plug into different training regimens. And it turns out that if we do that, then we actually will get a method or we'll have trained a neural network or a denoiser, so that if I keep iterating on this method, it's going to give me results that converge to a fixed point. There's some conditions attached to that, so we have to impose some constraints on our neural network as we're training it. And in particular, we need to make sure that it's not too variable, or in other words, it's got a bounded Lipschitz constant, which we can accomplish using some special normalization techniques. But the core message here is that with some relatively simple mathematical tools, we can set this up in a way that will guarantee that we're actually going to get a result that will converge if we run it for an infinite number of iterations. So I'm going to show you these things in action. So here's an image, and here's what would happen if we just did the inverse Fourier transform, where for all the Fourier coefficients we didn't measure, we just set them equal to 0. And this looks terrible, and it's just an illustration of how challenging this inverse problem is. But then we can compare the deep unrolling approach that we talked about earlier, and this new method based on fixed points that we call the deep equilibrium method. And if I zoom in on this cyan region here, what we can see is that this deep equilibrium approach gives us more accurate reconstruction of fine details in the image. And in addition, unlike the deep unrolling approach, which has terrible convergence properties, well, the denoiser that we've learned actually does lead to convergence. So I can run this as many iterations as I want, and I'm not going to have these divergence problems. Or kind of phrasing in another way, you know, here what we're showing is the accuracy of these three different methods that I've been talking about as a function of how many iterations I run. So first, there's the plug and play approach, and that's in orange. And we made the claim earlier that that method is inherently limited because it does not take this forward model or the physics A into account throughout the training. And we can see that numerically, that it does well, but never as well as the competing methods. In blue, we see the result of deep unrolled proximal gradient that's been trained to perform well after 10 iterations. And we can see after 10 iterations, then we do, you know, about 31 dB accuracy. But if we continue iterating past there, then our estimates start diverging and it looks terrible. But finally, in red, we've got the results of this deep equilibrium approach, which shows that as we continue to iterate, things converge. We're kind of holding steady in terms of the accuracy, and we converge to an estimate that's better than anything we were able to get with any of the past methods. Okay, so to wrap up here, I actually want to talk about some other ongoing active research directions in this broader community of machine learning and inverse problems. And I'm going to elaborate on each of these in a little bit more detail. The first of them is just trying to understand key trade-offs. So in particular, I talked about deep unrolling from the perspective of starting with a particular optimization algorithm, proximal gradient. But you could actually imagine using a different optimization algorithm as your starting point. And so this table that showed up in a review paper last year on deep unrolling just gives a smattering of some of the different approaches that have been explored. And you can see on this far right column a bunch of different optimization methods that people have used for their starting points. So things like iterative shrinkage and thresholding, or alternating minimization, alternating direction method of multipliers. So all of these are totally viable solutions. And all of them are doing the things that I said were necessary. They're incorporating this known A matrix into the training framework. But we really don't have a solid understanding of the trade-offs beyond that. Which of these methods require more memory? Which of these methods are more stable as we tweak different tuning parameters? Which of these methods perform better when we've got noisier data or when we've got fewer training samples? So far, the community has been exploring these different approaches and doing some proof of concept experiments, but we really lack a foundational understanding of the core underlying trade-offs. So a second active direction that I think is very interesting and important is trying to adapt to changes in the forward model. And this is something that certainly arises in applications like MRI, because there the A matrix, what we use to sense, corresponds to whatever knobs we turn on the MRI machine. And so depending on the doctor's orders, I might collect more Fourier coefficients, so have a longer scan, or I might collect fewer Fourier coefficients and have a shorter scan. Or I might change, or I might, have different scanners that all have different coil sensitivities. So it's entirely plausible that we would take any of these methods and train them on one particular scanner for one particular setting, and then later on need to be able to adapt them to a new scanner or a new setting. And if you don't think carefully about how to do the adaptation, things can go pretty badly. So for instance, here's an example where I trained this method based on deep unrolling for the setting where we've got 6x acceleration. So we only collect 1/6 of the Fourier coefficients. And we can see that the method we trained gets almost 30 dB PSNR. So it's working really well. It's giving us a nice accurate estimate. But now if I take that trained network and I say my forward model has changed because I'm going to collect less data or I'm going to collect more data, and I kind of replace the A matrix in those data consistency blocks with my new A matrix and then run it, then the result quality or the accuracy drops off precipitously. So I go from about 30 dB to here 28 dB, which maybe is not unexpected because I've got less data. But even when I've got more data and I've got a significantly easier problem that I'm trying to solve, my accuracy goes way down. So in contrast, I think one of the interesting directions in this field where my group's done some work, but there's other groups who are actively thinking about this, we could say, well, once I've trained a network for one setting, can I then adapt it to other settings in a principled way? And with some of the methods that we've been exploring, we see that that's indeed possible. And for instance, what we show is that when we get more data, we indeed do a better job at reconstruction, which is what you would hope, using methods that adapt to changes in the model, unlike the setting where we don't do any adaptation and everything falls apart when we make any changes at all. A third active direction is using machine learning to solve nonlinear inverse problems. So everything I've talked about today is assumed that there's a linear relationship between our data and our image. So y is equal to ax plus noise, and a is just a matrix. But there are many settings where we don't have a linear relationship, we've got a nonlinear relationship, and we'd still like to solve an inverse problem. So for instance, Berger's equations says, what I want to do is I want to find a function u that satisfies this partial differential equation. And so here's just an illustration of this from a paper by Racy from a few years ago, where the function of u and x is, the function u of x and t is illustrated in color here. And these little x's along the boundaries are points where we've collected data about the initial and boundary conditions. And so what people are interested in doing is saying, well, given these samples of the initial and boundary conditions and knowledge of the physics of the system, knowledge of the PDE in this case, can we figure out everything that's going on in the interior of the domain here? And it turns out that often that is possible. So these plots here are showing different cross sections at times 0.25, 1/2, 1/4, 1/2, and 3/4. And we can see even at different levels of smoothness or discontinuities, we're able to get very accurate reconstructions. And so ongoing work is really trying to explore, well, when does this work and when does it fail? They're also thinking about the best ways, similar questions to what we've been asking in imaging. What are the best ways to incorporate physics knowledge into the training process and into the reconstruction or inverse problem solving process? And then finally, another active direction that's being widely explored is a special kind of inverse problem that shows up in data assimilation. So here, our observations have a similar kind of form to what we've been talking about earlier, where y is perhaps a linear function of x plus some noise, and we want to recover x from y. But there's also some additional structure here. So instead of the x's now just being images with some known kind of geometry, rather they correspond to a time series that correspond to some sort of dynamics. And so in my picture here, I'm just showing the trajectory of a Lorenz 63 system. And so you've got these sort of 3D points, and each point corresponds to a different time. But we don't get to observe that directly. Rather, through H, through our observation matrix, we might only observe indirect observations of these dynamics. And so in this problem, the inverse problem is recovering X, even when we don't fully know the dynamics. And so our goal is to try to use the data and to design, for instance, neural networks to model the dynamics and to model the noise properties given observations Y. And so again, this is a real opportunity for us to use mathematics and statistics and ideas that have been developed over the past several decades and to integrate those with machine learning to do really remarkable things. So in particular, here's an example where the true dynamics are coming from a Lorenz 96 system. So we've got 40 different channels, and we can observe each one of them at each time here. And so you can see that there's some structure here, but at the same time, there's a lot of, it's highly dynamic. Okay, so what we did is we said, well, imagine now that we don't get to observe all 40 of these channels. We only get to observe about a third of them. Can we reconstruct the entire Lorenz 96 trajectory, or can we figure out what those underlying dynamics were, modeling them from a neural network? And so this is just a plot illustrating that this is indeed possible using these kinds of techniques. And in particular, what we did is we used, again, a classical method coming from the mathematics and statistics and optimization literature, in particular, the ensemble Kalman filter. And we used it as a frame, as an initial starting point. And then we said, within that framework, how can we replace kind of known things with neural networks and use that to train or learn the weights of the neural network? And one of the really exciting things in this area is that we can also use some of the auto differentiation tools that are built into neural network training software packages. And so what we can see is that these methods are able to make really accurate predictions, or they basically have really accurate estimates of the dynamics, either when we have no idea what the dynamics are or where we've only got sort of a rough, erroneous estimate of the dynamics that we need to correct. And in contrast, classical expectation maximization methods that don't fully leverage the power of machine learning tools get much, much worse predictions than we're able to achieve. So with that, I want to thank you again for the invitation to speak with you all today. It really was a huge honor, and I'm only sorry that I couldn't be there with you all in person, especially as you all head off to the wine reception now. But I'm very happy to have had a chance to talk with you, and I'd be happy to answer any questions.
Thank you so much, Becca, for a really fascinating talk, showcasing, I think, beautifully that with physics and mathematics and modeling, you can really design better learning models. So thank you very much. Thanks a lot. So are there questions, audience? Fine, just unmute yourself and ask. Or
you hear me?
I'm only catching about 50% of the words, but if someone's willing to take what you say and type it into the chat, I'll do my best.
Wondering, network. I think I used after training that each network is the same.
I'm sorry, all I heard was after training, each network is time. I know that's not what you said.
The that you just end up with one network with one set of weights?
Okay, I'm just going to take an educated guess here and hope I'm getting the right question. So, for instance, with deep unrolling, I've got multiple different pictures of a neural network here. And so you could say, well, should each one of these networks have its own independent set of weights, or should they all be forced to have the same weights? Is that the question?
Yeah.
Okay, so yeah, people have looked at both. And if you force them all to have the same weights, then that's called weight tying. And certainly that is what we have done in all the experiments that I showed today. We've done some experiments internally where we explored not doing the weight tying, and it didn't seem to have an appreciable impact on performance. So we really just didn't gain a whole lot by having the weights be different, but we certainly lost something in terms of interpretability, and we had more parameters to learn. So I don't think this is fully understood or explored. You know, people have done empirical experiments like ours in different settings, but you know, it all depends on how noisy the data is, how many training samples you have, what is the nature of the inverse problem. And so there's a lot that we don't really get about, you know, the role of weight tying. But yeah, like I said, in the settings that we have explored, it's made pretty minimal difference. And once we get into these, you know, deep equilibrium approaches that are based on trying to learn fixed points, well, then you really do have to have the same set of network weights for every iteration. And so when we do these experiments comparing these deep equilibrium models with methods where you have a fixed number of iterations and maybe the weights can change from iteration to iteration, we're still doing better with the deep equilibrium models. So this says to me that forcing the weights to be the same for every network is a perfectly fine thing to do.
Thanks a lot, Becca. There is another question in the chat.
Right. So thanks. So Soren says, are you able to ensure or encourage the existence of a fixed point? And yes, we can. So basically, we can show that a fixed point exists, and we can guarantee that we'll converge to it if this map, this f theta, is contractive. So what we need to do is we need to make sure that essentially the convolutional neural network that we train is contracted or has a bounded Lipschitz constant. So if the Lipschitz constant of this neural network is bounded, then the whole function we can show is contractive. And so the trick is to ensure during training that that we have this bounded Lipschitz constant. And so there are tools like spectral normalization that do allow us to force that. It's not perfect because the spectral normalization is essentially minimizing a loose upper bound on the Lipschitz constant. And so we end up being more conservative with this method than we need to be. And I think that, you know, this notion of trying to ensure the Lipschitz constant of a CNN is bounded has arisen in other settings as well. So I think there's ongoing interest in trying to get tighter bounds on the Lipschitz constant that'll make this whole process even better than it currently is. But nevertheless, with this approach, we can ensure the existence of a fixed point.
Or online? Maybe, Becca, can you understand me now well, or should I type my question?
Yeah, you sound really good now.
Okay, excellent. So my question is a more general one. So I guess there is a fine line between what you put explicitly into your model and what you make data-driven. And that is, you know, true for your inverse problem solution as well as for thinking about which PDEs to solve with classical methods, finite elements, let's say, Burger's equation you've shown before, and when to use learning. So what are your thoughts here? Is that something we at some point might be able to systematically decide?
Yeah, I mean, I think it's just going to ultimately be context dependent. I know that's not super satisfying, but you know, even with the methods that I described here today for linear inverse problems, I was just talking with a group at the Department of Energy, and they were interested in doing seismic imaging. And so for them, this A matrix, this forward model is huge. And so they're really attracted to methods that don't require any knowledge of the A matrix because they're of the computational burden of just using A. My hope is that there's something in between where you can have maybe approximations of A that are still, you know, easy to compute with and give you a boost relative to assuming you know nothing at all about A. And in the context of PDEs, I think it becomes even more complex. So for instance, in this paper, and I apologize for not having a reference to Racy's work on this, but one of the things that he, I think, initially proposed, which was really remarkable, was to say, you know, often what we try to do is we try to ensure that whatever our estimate, let's say U is a good fit to our samples at these points. But he says, you know, there's maybe lots of functions U that are a good fit to these samples at these points. What we want to ensure is that U is also a good fit to the PDE. And so he develops a loss function that explicitly accounts for the PDE, and he computes that using some of the auto differentiation techniques embedded in PyTorch and TensorFlow. And that produces really amazing results. It's also extremely slow, right? It's much harder to compute this PDE-based loss than to compute classical squared error losses. And so in some settings, you know, maybe it's easy to collect, you know, more data and more samples, whereas computing the PDE loss is a bottleneck. And in other settings, maybe collecting more data is a real challenge. And in contrast, computing the PDE losses is simple. So there's definitely like computational trade-offs there. In addition, I only kind of hinted at this, but there are other settings where maybe we know the PDE or some properties of the PDE, but we don't fully, but maybe computing this PDE loss is computationally prohibitive. So perhaps we know other things besides just the functional form of the PDE. So for instance, with nonlinear Schrodinger's equation, we know that there's a kind of scale invariance. And so, you know, I think there have been a series of papers that have said, well, if I know that there's some sort of invariance inherent with my PDE, can I impose those invariances as constraints on either the architecture or the training of my neural network? And so that's sort of a hybrid where perhaps we're not explicitly using the functional form of the PDE, but we are using, you know, properties of it to guide the design of our neural network architectures or to guide our training. And of course, if you don't have the invariances, you can't do that. So I don't know how easy it's going to be to have general principles, except in sort of like for certain classes of PDEs or certain classes of inverse problems. But I think it's a really rich and interesting problem space.
Thank you so much, Becca. Are there more questions? I think, Becca, we are slowly going to move towards the wine reception, which would be wonderful to have you here, but be sure that we will post on you.
Well, I'll make it a priority to visit Cambridge as soon as I can, and as soon as, you know, international travel is a little bit easier. I'm really sorry I couldn't be here in person today, but hopefully another time really soon.
All right, so let's thank Becca again.
Thank you.
Thank you so much, everyone. Thanks a lot also to the audience for coming and for hanging in there with us. Thanks a lot. Thank you, Becca. Good to see you.
Nice to see you too. Bye-bye.
Thank you. Bye-bye.
Wait.